Hi everyone, Dr. P here, and in this lecture video we'll take a look at another carbonyl condensation reaction, the Claisen condensation. So the Claisen condensation makes use of esters. So let's say we have ROC double bond O, CH, H. So we have some kind of acetate here. pK of one of these protons is around 24. And so we can go ahead and react that with, let's just do another molecule of the same ester. And we'll do this in OR minus, never in acid. Okay, so it's one thing about the Claisen condensation that's going to make it different than the Aldol that we've already seen, and the Michael, which will be in the next lecture video. Claisen will only occur in base. All right, so now what we end up getting now is ROC double bond O, CH, C double bond O, CH3. Actually, I should probably put this guy in red here because this is the new bond. Plus ROH. And then in a second step, we'll add H plus, and we'll get ROC double bond O, CH, C double bond O, CH3, which is a beta keto ester, or sometimes called a 1,3 keto ester. What that means is we have an ester here, and alpha beta, the beta carbon, has a carbonyl, a ketone, a keto group. Or we have 1, 2, 3 ester on carbon 1, ketone carbon 3. Now notice that this is 2 steps. So first we have to treat with base, and we want to match our base up with our ester, or else we'll hydrolyze the ester. And then we have to quench with acid. All right, let's take a look at the mechanism for this reaction. All right. So let's go ahead, and we've got our ROC double bond O, CH, and then we'll have OR minus come along and deprotonate, and then that will form our enolate. Alright, so what is this? This is our deprotonate to form enolate. And then we'll have our other molecule here, ROC double bond O, CH. So we will get nucleophilic attack. And that now gives us ROC double bond O C H H C O minus C. I'm just going to write that as CH3. I'm not going to draw out those hydrogens. And then OR. Now we can lose this leaving group, even though it's not a very good one. So we'll have loss of leaving group. Even though it's not a great leaving group, it can happen. And actually what happens after the leaving group leaves makes the reaction to go to completion. So let's just take a look at the species that we get. Sorry about that. And then we have OR minus. One thing to note here is that pKa of this guy is around 11. Okay, when we have a proton that's alpha to a ketone and an ester, it's around has a pKa of around 11, so it's pretty acidic. And this OR minus here is just going to pluck that guy off, and that will leave us with ROC double bond O CH double bond minus COCH3. Okay, and that was this species, whoops, this species here. I should put a minus sign there, actually. Okay, that's that species there. Is that guy right there. And then we'll go ahead and add H plus. So this part here is we'll call this a proton transfer. And we'll add H plus, and so these guys simply pull that, grab that proton, and we get our final product there. Let me see if I can squeeze all of that in. Okay, so this is a protonation. And it is a separate step in the reaction. All right, so my red pen is running out. Let me find another one. I think I have some in here. And oh, what do you know? I've got some of these red pens. I'll use one of these. Why not? These are a little nicer red pens. All right. So this is our mechanism. So remember, we deprotonate to make the enolate. So this is only going to happen in base. Then we get nucleophilic attack, followed by loss of leaving group. A proton transfer, which traps us in this following stabilized, well, it's an enolate, but it's a stable enolate because the pKa of that proton was 11. And then we add acid to get our final product, which is our beta keto ester. Now, notice how this is different from the mechanism of the aldol reaction. We are making the enolate, as we did with the aldol, by deprotonation. We also have nucleophilic attack. But with the aldol, we get a proton transfer to make the beta hydroxy aldehyde or ketone, as opposed to losing a leaving group with our Claisen reaction. All right. Now later on in an aldol condensation, you do lose OH minus as a leaving group, but that's after additional heating. Now sometimes with these reactions you can actually get a further reaction by treating with additional aqueous acid and hydrolyze and then heat, and you could get a decarboxylation. Although we tend not to not to do that too much, but I'll show you an example in just a minute. All right, so let's see here. Let's look at a couple more examples here. In particular, let's look at some crossed Claisens. Okay. Now remember, with the crossed aldol, we had to either use LDA to make all enolate and then add in our electrophile, or we had to use just a little bit of what was being turned into the enolate at a time. So what we want to do with our crossed Claisen is, again, to choose things carefully. In fact, let me grab the notes from last time here. Remember, to do crossed aldols, we either have to choose our enolate carefully or choose our carbonyl electrophile carefully, or actually choose both of them carefully, really. And so we'll do the same thing with our Claisen. So let's say we had acetone, so CH3, C double bond O, CH3. This is going to form the enolate. And then we will have, let's do methyl benzoate. So we've got our phenyl group there, our benzene ring, OCH3. So we'll treat this, and the way we write this out is 1 NaOCH3, that's our OCH3 minus base to generate our enolate, and then 2 will quench with acid, H3O plus. And in this case, what we end up with, because we used a ketone instead of an ester, so instead of having an ester react with another molecule of the same ester, we've got a ketone here which can only form enolate, and only forms one form of enolate, it's symmetric. And we have an ester here which has no alpha proton, so it can't form an enolate. So the only thing that can happen is we do get some enolate forming, we get the reaction, and we end up with CH3, C double bond O, CH2, and then our new bond here. I still have some stuff stuck on there. I like to point out the new bonds for you. And then we have C double bond O, PH. Okay, so that is a new bond. So just so you can see where things come from. And we lost this OCH3 as CH3OH as methanol. This is a beta diketone, also called a 1,3 diketone. So notice there's no ester in the final product here. Okay, we could have something like cyclohexanone, again symmetric, so we're only possibly going to get one enolate. And then we'll react this with the following species, which is sort of a diester, and I'm totally actually spacing out on the name for that. It'll come to me. I'll get you in the next lecture video. Totally spacing out the name for this diester, but we end up getting we'll have a new bond here, new bond, and then C double bond O O R. We'll get our beta ketoester. And actually, if you had an ester that you used to form the enolate, and then this diester species, you would get actually something that had a beta diester, or 1,3 diester. All right. Now, there's another reaction that I wanted to show you, which is a cyclic Claisen. This one is called the Claisen Condensation. So this is a cyclic Claisen. And actually, you know, I realized I forgot to talk about cyclic Aldol reactions last time, but I'll go ahead and talk about that after I do these, go through the Claisen condensation here. So we could have something like ETO, boom, boom. What do I have? 1, 2, let's do 1, 2, 3, 4, 5, 6, OET, double bond O. And then we'll treat this with NaOET and H+. So what happens? Well, where's our new bond going to form? Well, this is symmetric, so either those alpha, one of those alpha hydrogens or one of those will be removed. So let's just go ahead and take one of these guys, and then that alpha carbon will be our nucleophile, and it'll attack there. So now we'll have a new, you know, we can even number these here. 1, 2, 3, 4, 5, 6. So we're going to have ETO, boom, boom, 1, 2, and then we'll have 3, 4, 5, 6, and then our new bond is right here. And then we've got our double bond O. If we treat that with H3O plus and heat, we could drive off our a molecule of CO2. So we convert this to the acid, and then we could actually get that to leave as CO2 in a decarboxylation here. So I'll just put that in parentheses, okay? Let me number these carbons here, just like we did here. 1, 2, 3, 4, 5, 6. Just so you can follow along there, okay? Now, when you have the possibility to form cyclic molecules, 5-membered rings and 6-membered rings are preferred. Now in this case we can only form a 5-membered ring. But in the case of cyclic aldols, let's take a look at a cyclic aldol. So this is our cyclic Claisen. So let's just revisit aldols here. So let's say I had the following molecule. Let's say I had all right. And then I'll go ahead and treat this with NaOH. And the question is, what will I get? All right, so now I've got different alpha protons. In this case, again, the molecule is symmetric, so really it's just one end or the other. So I could get one of these guys deprotonated and then have this be my nucleophile that adds in there. Or I could have one of those guys be removed and this becomes my enolate and that would add in there. So let's take a look at what both of these products would be. And again, maybe I'll go ahead and number these. 1, 2, 3, 4, 5, 6, 7. Go ahead and number the carbons here. So in this first case, I've got 1, 2, 3, 4, 5, 6. A new bond between 1 and 6. So 1, 2, 3, 4, 5, 6. And here is my new bond. And then I will have, coming off of 6 there, so I've got 1, 2, 3, 4, 5, 6, 7. Now carbon 2 has my, excuse me, has my carbonyl. Carbon 6 had a carbonyl, but because I'm making that new bond, those electrons are pushed up onto the oxygen, so I end up with OH, like so. In this case, I'd have 1, 2, 3, 4, 5, 6, and then my new bond, and then I'd have 7, and I'd have my OH there. Let me number these here. 1, 2, 3, 4, 5, 6, 7. So this one would be the preferred product. Okay, and that's because we have the larger, more stable ring. We don't have any ring strain here. So again, 5-membered rings and 6-membered rings and 7-membered rings for that matter are pretty stable. So if there's a choice between forming a small ring or a 5 or 6-membered ring, you're probably going to get the 5 or 6-membered ring. If there's a choice between a 5 or 6-membered ring and like an 8-membered ring or something, then you're probably going to actually get the 6-membered ring instead of the 8-membered ring, although you could get the 8-membered ring. All right. I think those are carbonates. It just popped into my head. I think those are carbonates. Not related to, well, kind of analogous to the carbonate ion. Cover those up. That looks like CO3. But yeah, these diesters are also called carbonates. I think that's right. Anyway, so be on the lookout for cyclic aldols and cyclic Claisens. And in the next lecture video, we'll take a look at Michael reactions. All right, well, until then, stay safe out there. Bye now.